right. I'm moving on to the next section. The homework was done. Chapter 3 is done. And now it is understanding ownership. Expand that. This one I think is going to have a lot of reading in it. Okay, so the Rust programming language, the book. Understanding ownership. Ownership is Rust's most unique feature, and it enables Rust to make memory safety guarantees without needing a garbage collector. Therefore, it's important to understand how ownership works in Rust. In this chapter, we'll talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. It sounds like it's going to be a lot. Here we go. What is ownership? Actually, before we even, it's going to take us a while. We're going to do a number reading. Let me just make this nice, big. Boom. All right. What is ownership? Rust's central feature is ownership. Although the feature is straightforward to explain, it has deep implications for the rest of the language. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection that constantly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. All right, before we go into the third approach, let's talk about the first two. So garbage collection, like they said, it's like a point in time where a language, like let's say Python, for example, and Go has a garbage collector. A point in time where the garbage collector runs, it looks for all the memory that is no longer in use, and then frees the memory of that object or struct or thing that you have previously allocated memory to. And then in the second approach, where they were saying a program explicitly allocates memory and frees memory, from my understanding, that's how programming in C is done. I have not programmed in C myself, but from what I hear, you have to specify, you have to allocate your memory, and then when you're done with your memory, you have to free it. That is the programmer's responsibility. Okay, so Rust uses a third approach. Starting from here. Memory is managed through a system of ownership with a set of rules that the compiler checks at compile time. None of the ownership features slow down your program while it is running. So the need for that last statement is because traditionally with a garbage collector, the point at which the garbage collector runs typically slows down your application or slows down your program. I know that in previous versions of Go, not so much recently, people said they could notice when the garbage collector ran, like the program overall, like things would stop, things would get used too much, the CPU. It was just a noticeable bump in CPU usage. All right, continuing. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experience you become with Rust and the rules of the ownership system, the more you'll be able to naturally develop code that is safe and efficient. Keep at it. Thank you for the advice. When you understand ownership, you will have a solid foundation for understanding the features that makes Rust unique. In this chapter, you'll learn ownership by working through some examples that focus on a very common data structure, strings. All right, so we're going to work with strings to understand how ownership is dealt or handled, or what is ownership. But they're giving us this thing about stacks and heaps. Let me read through it, and then if it's too much, I'll just summarize. So, the stack and the heap. In many programming languages, you don't have to think about the stack and the heap very often. But in a systems programming language like Rust, whether a value is on the stack or the heap has more of an effect on how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter. So here is a brief explanation in preparation. All right, let's explain the difference between stacks and heaps. So both the stack and the heap are part of memory that are available to your code to use at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. This is referred to as last in, first out. Think of a stack of plates. When you add more plates, you put them on top of the pile. And when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing onto the stack, and removing data is called popping off of the stack. So this is a traditional stack structure. Last in, first out. So we just stack things accordingly, and you take them off the top. So the stack is fast because of the way it accesses the data. It never has to search for a place to put the new data or a place to get data from, because the place is always the top. Another property that makes the stack fast is that all data on the stack must take up a known fixed size. Okay, so just to be clear, what they're saying is that given that everything is stacked on top of each other in this stack, right, you never have to find the data. The data is always going to be at the top of the stack because that's the only place you push from. So you never have to search for the data. And because you don't have to search for it, it's reasonably fast, or extremely fast actually. Another property they noted is that all the data on the stack has a fixed size. So if it has a fixed size, that means the size is never going to change. And because it's never going to change, memory is never going to be moved. And the data will never be relocated and things of that nature. You never have a pointer to the data. You never have a pointer to the data and then find the pointer, then follow the pointer, things like that, things that could cost time. And because it doesn't have that extra stuff, it is going to be much faster than seemingly the alternative, which they're going to describe soon, the heap. All right, so continuing. Data with a size unknown at compile time, or a size that might change, can be stored on the heap instead. The heap is less organized. When you put data on the heap, you ask for some amount of space. The operating system finds an empty spot somewhere in the heap that is big enough, marks it as being in use, and returns a pointer, which is the address of that location. This process is called allocating on the heap. Sometimes it's abbreviated as just allocating. Pushing values onto the stack is not considered allocating because the pointer is a known fixed size. You can store the pointer on the stack, but when you want the actual data, you have to follow the pointer. So like I was saying earlier with the heap, because the data can move in size, you're going to have a pointer to your data instead of having access to that data directly. The pointer is used seemingly so that if at any point in time the data becomes too big for this original slot it had, then it can be moved to someplace else and the pointer just get a new pointer reference or a different pointer reference. All right, continuing. Now they're going to give you an example. Okay, think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds you an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you've been seated to find you. Oh, I understand it. Yeah, well, this is what I was talking about, the pointer. They can ask the pointer where you've been seated. The pointer will point you to the table where the memory is allocated. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all of the orders at one table before moving on to the next table. Taking an order from table A, then an order from table B, then one from table A again, and then one from table B again will be a much slower process. By the same token, a processor can do the job better if it works on data that is close to other data, as in on the stack, rather than farther away, as can be on the heap. Allocating a large amount of space on the heap can also take time. All right. When your code calls a function, the values passed into the function, including potentially pointers to data on the heap, and the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what parts of your code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often. But knowing that managing heap data is why ownership exists can help explain why it works the way it does. And finally, they will explain ownership rules. Ugh. It's a lot of preamble for this. All right, ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. 1. Well, I guess they're bullet points. So bullet point 1. Each value in Rust has a variable that's called its owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Okay, that's pretty simple. Variable scope. We've walked through an example of a Rust program already in chapter 2. Now we're past the basic syntax. We won't include they're not going to include the main function. So yada, yada, yada. We can probably skip that. As the first example of ownership, we'll look at the scope of some variables. A scope is the range within a program for which an item is valid. Let's say we have a variable that looks like this. And here's where I'm going to move this to the side. And here's where we have our editor. All right, so what they're saying here, at least in this example, let me scroll down again. Let's say we have let s equal hello, right? Basic syntax, seen this before, declaring a variable. The variable s refers to a string literal where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it is declared until the end of the current scope. Listing 4-1 has comments annotating where the variable is valid. So, like they were saying here, this is the scope from this curly brace to this curly brace. And after this curly brace, this s does not exist anymore. I guess one way to see that would be to, I'm sure they have another example later on, but if we wanted to mess around with it, we declare s there and then try to print s, and that should give us an error. Could not compile, understanding ownership, which is what I named the project. And then the error is s not found in this scope. So as you see, the scope for s right now exists from here to here. Outside of this curly bracket, s no longer exists. The memory for s has been redistributed or freed. So like they were saying in this example, which I just clearly demonstrated, in other words, there are two important points in this time here. When S comes into scope, it is valid. It remains valid until it goes out of scope, saying that if we wanted to print S here, say print line, do the same thing, right? S, and get rid of this. Let's comment it out. This should run, hopefully. Oh, it printed hello. Here we go. It ran. So while here S is still in scope, and then past this it is no longer in scope. All right, let's go to string types. The string type. To illustrate the rules of ownership, we need a data type that is more complex than the ones we've covered in the data types section of chapter 3. The types covered previously are all stored on the stack and pop off the stack when their scope is over. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data. Okay, so we want to store data on the heap, which means we want a data variable that can change in size. So something that is mutable for starters. We'll use string as the example here and concentrate on the parts of string that relate to ownership. These aspects also apply to other complex data types provided by the standard library and that you create. We'll discuss string in more depth in chapter 8. I hate it when they do that, but they do that a lot. Well, to be explicit, I hate it when they say, we'll do this, or we'll learn about this later on. Learn about this later on. We'll learn about this later on. Don't worry about it now. Don't want to tell me about it. Anyway, we've already seen string literals, where a string value is hard-coded into your program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they're immutable. Another is that not every string value can be known when we write our code. For example, what if we want to take user input and store it? For these situations, Rust has a second string type, string. This type is allocated on the heap and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function like so. Okay, so in summary, what they're saying is that yes, this is a string. However, this is a string literal and it is immutable, so it's not going to change. We can't like add words to it or take away letters from it. And because it's immutable, it's stored on the stack. It has a fixed size, so we pop it onto the stack, and then we push it onto the stack, and then we can pop it off. But that's not great for every situation. There are some situations where we may not know the size of the string, but we have to store a string. In that case, we want something that can change in size. If the string changes in size, that is going to be stored in a heap. And for those situations, we have a new string type, which we can create by using the from function. So let's try that. Just write that right here. String, which is from the standard library. I believe it's by default already imported in, so we don't have to import it, but I guess if you really wanted to, you could. From, and you can already see that this has changed. So this is no longer a pointer to a string. This is string type, capital S. So for emphasis, let me just comment this out and show you what that looks like. So originally we have this, right? We have a pointer and we have lowercase str. But as soon as we use the string from, the type has changed for this variable. Just something to note. All right, so the double colon is an operator that allows us to namespace this particular from function under the string type rather than using some sort of name like string underscore from. We'll discuss the syntax in the method section of chapter 5, and we'll talk about namespacing with modules and paths of blah, 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 blah. We'll talk about this later. That's all they're really saying. However, this is a module. I believe we could import it. I forgot how importing works in Rust, but we'll cover that later. And then once you import something, if you want to call a method from it, then use this syntax. You're just accessing a method or a function within that module. So this kind of string can be mutated, and they would like to demonstrate that. So this sort of string, we have hello, and we can do s dot. Looks like we have push string, which has a signature for just a string, I guess. Yeah, it's just a string. It's same type, because it has to be the same type in Rust. That makes sense. Put that there. Oh, I forgot the mutable. Haha. And now if I run this, it should say hello world, which works, and it's within this scope. Outside of the scope, it does not exist. All right, so what's the difference here? Why can string be mutated but literals cannot? The difference is how these two types deal with memory. Memory and allocation. In the case of a string literal, we know the contents at compile time. So the text is hard-coded directly into the final executable. This is why string literals are fast and efficient. But these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into a binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. Okay, so that makes sense. What they're saying here is that when you have a string literal, since it's known at compile time, that string is saved in the binary that is created when Rust compiles. So it doesn't have to do anything with it, it's just there. However, if your string is mutable, that means it can change over the course of time, and you can't save something that changes during runtime. You won't know that state. Runtime is during while a program is running, and compile time happens prior to that. Prior to that running, you won't know what state the string is going to be in, a mutable string. With the string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap, unknown at compile time, to hold the contents. Yeah, so what I was saying, at compile time, you cannot know how the string is going to be mutated. What is it going to grow? Is it going to shrink? So at compile time, all you can do is allocate a piece of memory where that string is going to be saved. This memory must be requested from the operating system at runtime. We need a way of returning this memory to the operating system when we're done with our string. Okay, so the memory that is used, the memory that is requested for this unknown size, this mutable thing, seemingly is requested at runtime. So at compile time, you know that you're going to need to make a request, and while the program is running, at that point in time, it makes the request to the underlying operating system for a piece of memory to use. And then when it's done, it has to return that memory to the operating system. That's probably done via the ownership property or ownership feature of Rust. The first part is done by us. So when we call string from, this implementation requests the memory it needs. This is pretty much universal in programming language. However, the second part is different. In languages with a garbage collector, GC, the garbage collector keeps track and cleans up memory that isn't being used anymore. And we don't need to think about it. Without a garbage collector, it is our responsibility to identify when memory is no longer being used and call code to explicitly return it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. So what they're talking about here, kind of harping on, is a lot of issues you see in other, well, mostly C, seemingly C, where you have to do the cleaning up yourself. If you try to free memory before it's allocated, then that's an issue. If you try to free memory twice, then at the second time you try to free it, it doesn't exist. So that's an issue. And if you never free it, then you're wasting memory. So this ownership feature is seemingly going to take away that worry and concern from us. They're going to do it for us at compile time. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from listing yada yada yada. So here they have another example. They have the string valid from this point, scope do stuff no longer valid, and we can see that by just moving this Control X. If we put that here and try to run it, it will tell us S is not found in this scope because this scope ended. This is a natural point at which we can return the memory our string needs to the operating system. When S goes out of scope, when a variable goes out of scope, Rust calls a special function for us. This function is called drop, and it's where the author of string can put the code to return the memory. Rust calls drop automatically at the closing curly bracket. Alright, so there seems to be an explicit function used to free up the memory, just like they were expressing in C, but instead of it being free, it's called drop, which they illustrated here. And seemingly we can probably do that ourselves, but it happens automatically when a variable goes out of scope. So we don't have to do it. And they give us a note. Note, C++, this pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition is initialization. That's a weird name. Rai. R-A-I-I. Huh. The drop function in Rust will be familiar to you if you use Rai Patterns. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated on the heap. Let's explore some of these situations now. Alright, so they have a new example. Let's get away from this. Let x equal 5. And then we're saying let y equal x. Alright. So you probably guess what we're doing. We're binding the value of 5 to x and then making a copy of the value of x to bind it to y. Now, we now have two variables, x and y, and both equal 5. This is indeed what is happening because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. I see what they're talking about here. So seemingly, if a value is of fixed size and immutable, like an integer is, we can say x equals to 5, and that's going to push something onto the stack. We can say that y equals to x, and instead of being a same pointer, it's actually going to make this 5 value and also push that value onto the stack. So seemingly we have two values onto the stack. So x equal to 5 is equivalent to y equals to x is equivalent to y equals to 5. Whereas in other languages that might be different. In other languages, we might, if we change the value of x, in other languages, if we change the value of x, the value of y should change as well. Let's test that theory out. So we're going to print out x and y, right? X equals y equals x, y. Because now I'm curious to see what happens. Run this real quick. X equals 5, y equals 5. Now, if this next line, if we said let x equal 6, this is technically a new variable because it's shadowing. We're redeclaring x. So we're not changing the value of x. X is immutable. In this situation, what should y be? Y is still equal to 5. So yeah, like they were saying over here, they pushed 2 values of 5 onto the stack. Okay, I like that. That's consistency. Now let's look at the string version. So the string version is going to be us examining what happens when you put things, when you allocate onto the heap. So let s1 equal string from, and they have hello. That works for me. And then we're going to probably say let s2 equal s1. And for clarity's sake, let's print these things out. S1 equals comma, S2 equals S1, S2. Make sure everything runs. Says it could not compile. Ooh, that is different. All right, let's see what the explanation is. This looks very similar to the previous code. So we might assume that the way it works would be the same. That is, the second line will make a copy of the value in S1 and bind it to S2. But it isn't quite what happens. Okay? So what they're doing there is calling out my assumptions. I thought this would work. It doesn't work. S1 is defined. S2 is not a copy of S1, and now we have an issue. So take a look at figure 4-1. I guess that's here. To see what is happening to string under the covers. A string is made up of 3 parts, shown on the left. A pointer, okay, a pointer to the memory that holds the content of the string, a length, and a capacity. Okay, so S1 is a pointer to piece of memory. It is a length, how the size of that memory, which hello is 5 characters, and capacity, which if it were ever to expand, if that's how much it can expand. Right now it's at max capacity. So we have those 3 properties, right? The length is how much memory in bytes that content of the string is currently using. Yeah. Capacity is the total amount of memory in bytes that the string has received from the operating system, so how much space it can use. The difference between length and capacity matters, but not in this context, so for now it's fine to ignore the capacity. I do not agree with that. All right, so let's talk about capacity. So let's say we have a stack or array. We already talked about stacks, they were explaining it here. Let's say we have a stack that has 2 items in it, or a stack that we say is of size 5, as in it has 5 boxes. That would be the capacity. However, all these boxes do not necessarily have to be filled. If we want, we could just put things in box 1 and box 2. And now our length is 2, but our capacity is 5. So what happens seemingly when you get max capacity? Well, then you have 1, 2, 3, 4, 5. That means all 5 boxes are filled. In terms of a stack or an array, or traditionally in programming arrays, right? As soon as you try to add a 6th item into your array, given that it's mutable, the programming language has to request a different piece of memory, a larger piece of memory, to put your 1 through 6 items in. So this box that started out with 5 is like, no, 6 items don't fit in here. I'm gonna need to do something else. So then you find a new piece of memory. Let's just double it. We went from 5, now we have a capacity of 10. And all the items from the 5 box has to be copied over to the 10 box. So then 1, 2, 3, 4, 5 get copied over to the new array of size 10, capacity 10. And the first 5 slots are filled. And now your 6th one goes in. And now you have the first 6 slots filled. And now your length is 6 and your capacity is 10. So the difference between capacity and length is how much space you're actually using, and capacity, how much space you're allowed to use before you run out of memory. Allotted memory. Now that that's over with, let's continue. So, when we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like this. So this is what happened. We define S1. S1 is going, bloop, here's the memory, size, capacity, whatever. Then when we get to S2, we're like, okay, here's the pointer to the same piece of memory. Here's a pointer to the same piece of memory. That's probably where the issue is. The representation does not look like figure 4-3, which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 equals S1 could be very expensive in terms of runtime performance if the data on the heap were large. So what they're saying is, this is what it looked like if they just copied the underlying data, the data that was allocated to S1, they made a new copy of it and allocated that to S2. So this would be a piece of memory, this would be a piece of memory, and this is just a copy. This, I shouldn't do that. This is a copy of this. But what we have in actuality is this. We have one allocation of memory and 2 things pointing to it. Earlier, we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4-2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as double free error and is one of the programming safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. Okay, completely understood now. The reason why this is an issue is because we have 2 variables pointing to the same piece of memory, but our ownership rules state that as soon as these variables go out of scope, they have to be freed. And they're going to be freed with drop. Drop is going to be called on both of these, which means that since they point to the same point in memory, drop is going to be called twice on the same point of memory. It's going to try to free this point of memory twice. When it does it the first time, it's okay. When it does it the second time, that is a bug. And Rust is not going to let us do that. Hence the error. To ensure memory safety, there's one more detail to what happens in this situation in Rust. Instead of trying to copy the allocated memory, Rust considers S1 to no longer be valid, and therefore Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to run the code. Yeah, I did that already. And then this is the error I got. Value moved here. Value borrowed here after moved. So what they're telling me is that at this point in time, right here, S1 is valid. We can use it, we can print things, we can print out S1. At this point in time, S2 is valid, but S1 goes out of scope. It is, well, not out of scope. It is no longer valid. They've dropped it. So if that is the case, if we remove S1 here and only look at S2, then this should compile. We have S2 equal to hello. If you've heard the term shallow copy and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable, instead of being called a shallow copy, it is known as a move. In this example, we would say that S1 was moved S1 was moved into S2. So what actually happens is shown here. S1 was moved into S2. So in other languages, where they mention shallow copy is where this is true, exists and you can use it. This exists and you can use it, but they both point to the same points of memory. The same point. They point to the same point of memory on the heap. That is a shallow copy. A deep copy, because they didn't define it there, would be what they had here. This would be a deep copy, where we say that S2 is equal to S1, but they no longer point to the same point of memory. They have their own point of memory that they point to that is independent of each other. So if you were to change S1, that would not affect S2, and if you were to change S2, that would not affect S1. That's a deep copy. In the shallow copy example right here, given that this is still valid, if you were to change S1, that would also affect S2, and S2 would be changed, and vice versa. So that solves our problem. With only S2 valid when it goes out of scope, it alone will free the memory, and we're done. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Ways variables and data interact. Clone. All right. I guess since we got into the topic of copying, now we have to talk about cloning. If we do want to deeply copy the heap data of a string, not just stack data, we can use a common method called clone. We'll discuss method syntax in chapter 5, but because methods are a common feature in many programming languages, you've probably seen them before. Here's an example of clone. So if you want this example to work as it was before, let's write S1 equals to this and put S1 here. If you want this to work, we have to clone S1. And let's make sure it works. Yep, cloning. This works just fine and explicitly produces the behavior shown in figure 4-3, where the heap data gets copied. Let me just scroll back up so you can see that real quick. So that is this figure. This is a deep copy. This is what a clone does. When you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It is a visual indicator that something different is going on. All right, stack only data copy. There's another wrinkle we haven't talked about yet. This code uses integers, part of which shown in listing 4-2 works and is valid. Okay, let's go back to the original integer example. So they have let x equals 5, let y equal x, and they have the print. Get rid of that I. run that real quick. So this compiles, this runs. But this code seems to contradict what we just learned. We don't have a call to clone, but X is still valid and wasn't moved into Y. The reason is that types such as integers have a known size at compile time and are stored entirely on the stack. So copies of the actual values are quick to make. That means there's no reason why we would want to prevent X from being valid after we create the variable Y. In other words, there's no difference between deep and shallow copying here. So calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. So what they're saying here is what I said earlier. Because this is on the stack, they know it at fixed size, and the cost of just making a deep copy of it is insignificant. So they do. So X is equal to 5 and Y is equal to 5. It says X, but really they just put another 5 on the stack. Rust has a special annotation called the copy trait that we can place on types like integers that are stored on the stack. We'll talk more about traits in chapter 10. Chapter 10. If a type has a copy trait, an older variable is still usable after the assignment. Rust won't let us annotate a type with the copy trait if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the variable goes out of scope and we add the copy annotation to that type, we'll get a compile time error. To learn about how to add the copy annotation to your type, see derivable traits in Appendix C. That's even farther than chapter 10. Wow. All right. So what types are copy? You can check out the documentation for the given type to be sure, but as a general rule, any group of simple scalar values can be copied, and nothing that requires allocation or is some form of resource is copy. Here are some of the types that are copied. So what they're saying here is they have this trait called copy. If this trait exists, then you can do this thing with it. It makes a copy. It's allocated on the stack. Sorry, not allocated on the stack. It is memory is on the stack, and because it's on the stack, it's cheap to make copies. And because it's cheap to make copies, they just make copies of them. And we can. They haven't told us about traits yet, but there is a copy trait that denotes this property. Right now, they're trying to give us a general idea of all the other types, or at least some other types of data that have this trait. All integer types, Boolean types, all floating point types, all char types, tuples if they only contain types that are also have copy. So yeah, tuple. Given that everything inside the tuple is also allocated on, sorry, not allocated. Everything inside the tuple is also on the stack. Oh wow, this is long. Okay, but we're almost done. Almost done. Ownership and functions. The semantic for passing a value to a function are similar to those for assigning a value to a variable. Passing a variable to a function will move or copy just as assignment does. Let's see what they have in this example. Kind of curious. No. So they have let s equal string from, make this hello, and they created a function down here called take ownership. It takes ownership. some string, and type is string, and it doesn't return anything, and we're going to print something. They have another function down here saying makes copy some integer I32 print let me fix that syntax. Okay, so we have a string, and then we want to pass it into take ownership, pass s in, and then we're declaring a variable, an integer, and we'll pass that into makes copy. And then we have this documentation over here. So let's run this and make sure it runs. We have hello, we have 5. And let's make this bigger so we can see what they're talking about. All right, so the first line. Oh, it went down. Okay, here we go. Here we go. First line, we define the variable, right? S comes into scope. Then we say it takes ownership. S's value moves into the function, and so it is no longer valid here. So S's value moves into this function, and is no longer valid in this scope passed here. So it prints out here, but if we were to write a print here, right under take ownership, this should fail. And let's test that out. So since S goes into here, this function is taking ownership of S. If we were to say print S here, this should not compile. Yeah. So the value was moved here as an S went into here, and it was moved into this function, take ownership. But we tried to print it here, but the value was already borrowed here after moved. The value is no longer there. Okay, that makes sense. Let's get rid of this. What else does it say? So S comes into scope here. Sorry, X comes into scope here. We make a copy of it. So X would move into the function, but I32 is copy. So it's okay to still use X afterwards. I see what they're saying. So if the variable that you're using, the type, has the copy trait, then when you pass it into a function, you're not passing the ownership of it into that function. You're just making a new copy of it and then passing that copy in. So with that being said, if we were to change the value of X within this function, no one would be the wiser. So let's say some integer, because X is going in here. Some integer. Oh, they're mutable, so you can't really change. You have to redefine it. And this would be shadowing, so it shouldn't make a difference. Some integer +1. And then right here, you see, just to verify that we can still use X, print X. So you have 6 being printed out because of this. We did some integer +1, which is this is the copy of X that's being passed into here. And this is shadowing, so we're redefining with some integer to be some integer plus 1. 5 plus 1 is 6. And then after that, we still have access to x because we're printing it out here, and that is right there, the 5. Okay. And then x goes out of scope at this line because this is the curly braces. Then s, but s value was moved. Nothing special happens here. So x goes out of scope here, and nothing happens with s because s has already been moved. It got moved into here, and thus s goes out of scope here. Okay. Okay. And then they're saying what we already tried. If we try to use s after the call to take ownership, Rust will throw a compile time error, which we saw. Alright, so let's see what the next example is. Return values and scope. Returning values can also transfer ownership. And here's our example. So let's erase this stuff and write our new stuff. So we have let s1 equal, they have a function called gives ownership. Takes in 0 parameters and outputs a string. It says let some string equal string from, I really like the word hello. Some string. So here we're defining some string, and then here I believe the term is expression because it does not have this thing after it. It is being returned because all expressions return something. So now if we say gives ownership returns a string, and now s1 is equal to that string. If we were to put that there, then we will get an error. Let me take that out. Okay. So then here they have let s2 equal string from this is hello again. Okay. S2 comes into scope. Let S3 equal, another function we have not defined. Function takes and gives back. Okay. And let's scroll down so we can see that function definition. Function signature, I should say. A string, which is going to be of type string, and we're going to return a string. A string. I see what they're doing here. So we're passing in a string, seemingly s2. So let me takes s2. We're passing in s2. So this is taking over ownership. S2 goes in here. And then we're returning S2. So we're passing S2's ownership to this thing, to S3. Okay, and this is just compile. We have a warning, unused variable S3. S3 is not used. Get rid of that by just printing S3. Print S3, and to make it unique, just call it hello2. Hello2. to you. And we have hello to you. Oh, another unused variable one. S1. Yeah. How the cookie crumbles. All right, let's continue. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop, unless the data has been moved to be owned by another variable. Okay, so they're using the official terms. All right, so taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. It's possible to return multiple values using a tuple, as shown in listing 4-5. All right, so now we've got an example where we return multiple things. Let's get rid of all this stuff. S1 still exists. S2 is being defined by something else. Oh, all right, so let's write this function first. Function, we have calculate length. It takes in a string and it returns a tuple of string and usize. So one thing to note, given that this tuple has a string type in it and string type is allocated to the heap, this does not have the copy trait. Just something to point out. So let length equal to s dot length, and that's going to be the u size, and then here's what we're returning. S length. And up here we're saying that S2 and to calculate, and then we pass S1 in here, and then we want to print that. Print the length of is S2 length. Run that real quick. We have an arrow. Do they tell us? Oh, give ownership. That doesn't exist anymore. This is now string from and hello. The length of hello is 5. Oh, I think that's the end of this section. Let me just verify. What is ownership? Yep, we have come to the end of this section. The next section is references. With that being said, this was a long one. I hope you guys understood this. I hope this was clear. Hope this was useful. With that being said, peace.